Hello. I'd like to talk with you about linear approximation, the super cool use of the derivative to be able to approximate values of things quickly and without a calculator. It's so awesome. So check it out. Recall that for a curve, the tangent line is the line that just touches at that one point. At that one point. What makes this line so special is that it touches at only one point, and that no other line fits any better. And then if I zoom in on this curve, the difference between the tangent line and the actual curve becomes vanishingly small. That I can't tell the difference between my curve and the actual, between my curve and the tangent line, okay? What this means is that we can use this. So suppose that we are here at this value. That's our special value a, and I want to figure out what the height of the function is at some distance delta x away from a. Okay, so I want to know what the height is right here. Okay, the height of this is f at a. Which maybe if I don't have a calculator is going to be hard to compute. But check it out. The point on the tangent line right here is about the same as the value of the function itself, and the difference right here, which is the error is small. Okay. So what we're going to use is that the tangent line is about the same thing as f of x near a. Now, I think of a as a point of linearization. Okay? The point of linearization, because what I'm going to do is I'm going to be like, oh, well, working with a curve is difficult, but working with straight lines is really easy. So if I want to compute that should be f of a plus delta x. I do apologize. Right, because I stepped further over, the height of this one right here is f of a. Come on. Okay, so I want to compute f at a plus delta x, and that's hard, but that's about the same thing as f of a plus f prime of a times delta x. Because I start here, and I do rise over run. And what is the rise and the run? Well, the run is delta x, and the rise is, the slope of this line is f prime at a. And then, so that would be the rise if I was going over 1 unit, but I'm going over delta units, so I have to scale it by delta x units. Okay. So I can approximate my function by using the tangent line and the delta x distance that I need to get there. So what I'd like to do is I would like to wipe this diagram and do a problem to make this really come alive. Okay, so I don't have a calculator with me right now, at least not one in front of me that I'm going to use to do this. So I want to compute the cube root of 8.1 without a calculator. I and without a fancy algorithm for computing third roots. Okay. Well, what I want you to notice is that 8.1 is about equal to 8, and that 8.1 is equal to 8 plus 0.1. So why am I choosing to do that? Well, I happen to know the cube root of 8 is equal to 2, and then this part right here is going to be my delta x. So a is going to be equal to 8, and then delta x is going to be equal to 0.1. Okay, so what I'm going to do is I'm going to take the cube root function and what I want to know is I want to estimate f at 8.1 that's equal to the cube root of 8.1, and that's going to be about equal to an approximation. Okay, that's about equal to, well, what do I do according to this thing right here? F at a. So that's about equal to the cube root of 8 plus, now I need f prime at 8 times 0.1. Because that's going to be the slope times how far over that we're moving. Okay. So I need f prime at, nope, I need, well, I do need f prime at 8, but first I need f prime. X to the 1/3 prime is 1/3. X to the minus 2/3. Regular old power rule, which means that f prime at 8 is equal to 1/3 of 8 to the minus 2/3, which is 1/3 times 8 to the 1/3 squared to the minus 1. So I just decomposed that minus 2/3 into steps that I can handle. I don't know the square root. Sorry, I don't want to deal with cube roots of a large number, 64. So I think I'd rather deal with something that I already know the cube root of. So I happen to know the cube root of 8. So that's equal to 2, because 8 to the 1/3 is 2. Squared to the minus 1 is equal to 1/3 of 4 to the minus 1 equals 1/12. So this here is 1/12 times 0.1. Okay. So I know that the cube root of 8.1 is about the same thing as 2 plus 1/12 times 0.1. So that's 2 plus 1/120. And 1/120 is somewhere around 0.01. Okay, so I do happen to have a calculator here. That's 0.00, 2.008, 333333333. And the actual answer is the cube root of 8.1 look at this. The cube root of 8.1 is equal to 2.00829.885 and some stuff. Look how close we were. Look how close we were. This is so cool. Okay, so if I could just remember 1 over 120 is this number right here. And I feel like there's a way I probably should be able to remember that. I don't know. But I don't have that one memorized right now. But that's okay. So what's so cool is that the method for estimating right here uses a base point about which I know f of x, right? So we're doing cube roots. And there's a nearby cube root that I know. I know the cube root of 8. And then I don't want to deal with the 0.1, so I'm going to be like, okay, well, we'll just do linear approximation. So now we need the slope of the tangent line. I found that the slope of the tangent line was a 1/12. And how far are we going along the x-axis, delta x, 0.1, okay? So I can estimate some value by taking the actual function value at some convenient base point plus slope times how far you're going in that direction. And that's one of the coolest ways to use linear approximation for estimating values. Oh, love it. Okay. Okay. Thank you very much. I appreciate your time today, and I will see you for our next video together. Bye.